Thanks for David's introduction. Yeah, it's a good chance for me to share my research study using the machine learning method to track the climate drivers of wind yield shock at the Europe. And as we know, climate change has posed a great challenge for the global crop production. Many studies have evaluated the climate effects on the extreme climate events on crop yield. But in turn, when extreme low yield occurred, we also want to know the climate driver of that events, because extreme low yield or yield shock have a great effect on the food supply. And if we can better understand its climate drivers, we can design better adaptation strategy to minimize the crop loss effect. So in this study, I will use the machine learning method to identify the main climate drivers of wheat yield shock in Europe. And here its study shows a good example to identify the climate driver of wheat yield shock in Europe. This year, it's very severe yield shock in France wheat. We can see most of the yield has dropped to a very low level. But most process-based models can't forecast these yield shock events. And this study uses a statistical model trained with the yield shock events. And the statistical model shows some better performance than the process-based model. And when they do the attribution analysis, it finds the yield shock is primarily driven by the compound extreme warm winter and wetter spring. So this study shed light on how to use the statistical model to better understand the climate driver of yield shock events. And this figure shows our study's framework. And the left box is based on the yield shock analysis with the subnational yield survey data, and the right box is based on the same time period yield model, the yield data based on the crop simulation. So we can evaluate whether the current crop-based models can have consistent results with the yield survey data. Firstly, we identify the yield shock events based on the yield data. And then we train a reinforced model based on the climate variables to predict the yield shock probability. Because the reinforced model has a good capacity to capture the nonlinear response to the climate variables. So here, it shows the yield shock identification. We use the 10 percentile to identify the yield. That means the yield shock is treated as a dummy variable. So when the yield shock occurs, it is 1, otherwise it's 0. And finally, we use the Shapley attribution analysis to decompose the total yield shock probability into each climate drivers. We also do the future yield shock prediction with the future climate data set, and then do a future attribution analysis with the Shapley model. The same procedure was applied to the yield shock identified in the crop simulation. So we want to know whether the crop model have a good capacity to simulate the yield shock. So firstly, let's see what kind of climate variables has been used for the reinforced model. So totally we used 20 climate variables as the predictor. The 20 climate variables are created by integrating 5 types of climate variables over 4 wheat growing seasons. The 5 climate variables generally characterized like the warm days, cold days, and daily precipitation. Also the rainy days, because rainy days means the number of days with precipitation. It's a little different from the precipitation number. And also we included the potential evapotranspiration. It characterizes the water demand from the atmosphere. So here we also consider the 4 growing period to better characterize the climate effects on the wheat yield, because many studies have suggested climate effects on the crop yield that depends on the timing of the climate variable. The fall seasons are generally defined based on the critical winter phenology, like the fall winter growth period and the winter dormancy period, and also vegetative period and the reproductive period. So we totally have 20 predictors for the random forest model. With the random forest, our random forest model is trained for the 4 regions because we want to better capture the potential differences in farmer management practices in 4 regions. For example, the different region might have different levels of irrigation, or they use different kinds of cultivars. And the cluster, we can see the cluster of the 4 of the countries into 4 different regions are generally based on the geographical location. And the yield shock is defined with this equation based on the relative yield anomaly. So that means with yield at the department I, we get its expected value, use the loss regression, and then we get its relative yield anomaly. So yield shock is defined as the lowest 10 percentile of yield shock, of the relative yield. This histogram shows the distribution of relative yield anomalies in each region. And the vertical red line is the 10 percentile that is used as the threshold to define the yield shock for each region. So when we have the yield shock, and we can analyze its spatial and temporal pattern of the yield shock. Here we can see that here is the spatial pattern and temporal pattern of the yield shock. The left shows an error fraction of the wheat yield shock over time. We can see it shows a slight increasing trend. And the right figure shows the spatial pattern of yield shock frequency. The spatial pattern of the yield shock frequency suggests the yield shock is more frequent in the southern Europe, like Spain and South France, and also the Eastern Europe. Okay, so let's see the next. With the climate predictors and identified yield shocks, we can build a random forest model for each region. We use the cross-validation model to tune the critical parameter in the random forest model. And then we use a partial dependence plot to show how yield shock probability changes with the climate variables. So we can see generally in the left panel, it's the yield shock prediction with the yield survey, and the right is based on the crop models. So we can see generally the warmer days correspond to a higher yield shock probability, but the crop model shows a weaker response for warmer stress. And for the precipitation of rain days, the random forest based on the yield survey suggests both low and high precipitation of rain days corresponds to a high yield shock probability, but the crop model can just capture the low precipitation of rain days effects on the yield shock increase effect. So that means the crop models might have a bias for the future yield shock probability prediction in crop models. And so when we use the partial dependence plot, we can have an overview of how yield shock probability will change with the climate variables. But for each yield shock event, we still don't know what's the relative contribution of each climate variables to the total yield shock probability. To answer this question, we used a Shapley-based model. Shapley model is approach based on the cooperative game theory, and the model can capture each feature's contribution to the single prediction. Here it's the shock prediction, the shock probability, and then the Shapley value is calculated to measure the average, the marginal effect of predictor across all possible correlation. Here it's a simple example. The random forest model predicted that the yield shock probability is about 0.8. And then the Shapley model can decompose the total shock probability into each climate stress contribution. So we can know which climate stress is the primary contributor for these yield shock events. And this table shows the 5 climate drivers of yield shocks we considered in this research. So with the Shapley model, we can get each variable's relative contribution, and then we can define or we can identify or define the primary climate driver. If like this variable has the largest contribution to the yield shock probability and also corresponds to a abnormally high or low value, and then warm days will be identified as the yield shock driver. But for warm days, we don't consider the low value because only high temperature normally corresponds to a high probability of yield shock. But for precipitation related variables, we also consider both low and high value. That means that corresponds to the excessive water supply and low water supply. That will have a comprehensive evaluation of how climate effects drive the yield shocks. So here, this figure shows a summary of the primary climate drivers for each region in Europe. So our attribution analysis suggests that during the total 40 years, the low water supply is the most pervasive climate driver of yield shocks, and followed with the extreme warming and high water demand and excessive water supply. But the dominant climate drivers varied for each region. And we can also find there has a distinct spatial pattern about the yield shock driven by low water supply, because we can see in the relatively dry and warmer area like the South and East Europe, the yield shock is mainly driven by the low supply in this area, relatively with the North and West Europe. And when the total time period is decomposed or divided into two time periods, we can see there is a distinct shift. The primary climate driver shift from the later time period, from the early time period, which is driven by the water supply, driven by the low water supply, and then in the later time period, it's primarily driven by the extreme warming. That means the primary driver shift has already changed, probably because the climate warming has already bring more extreme heat stress in this area. And then let's see how the yield shock prediction and the attribution analysis performed in the core model. So we can see most of the yield shock in the core models are attributed to primarily driven by the low water supply, which is about 2 times of that in the yield survey data. This means the core model has overestimated the yield shock effects by the low water supply, which will bias the future projection. And here is the future prediction based on the random forest model. We can see in both scenarios, there has an increase in the yield shock probability, and the spatial pattern suggests that the yield shock increase is the largest in this eastern area, like the Hungary and Romania. And then let's see the yield shock probability in the future when we do the attribution analysis, how the primary climate driver have changed in the future. We can see there is a distinct increase for the primary driver of extreme warming in both scenarios. That means Eastern, and also we find the Eastern Europe has the largest increase. This probably explains why the high yield shock has increased most in the spatial pattern. Okay, so that's all of my study, and thanks for your attention. And I'm happy to take the questions.
Yes, thank you, Peng. So we have time for a couple of questions. So please write it in the chat if you. I have one question for you, Peng.
Yeah.
Can you say something about computation time?
Oh, the computation.
How long did computation time for all these simulations?
Because I use a cluster to do the attribution analysis. The model training it's about 5 or 10 minutes, depends on the regions. And for the attribution analysis, it's a little time consuming because it do all the compute combination of the variables. So it for each region, it's about 1 hour for the cluster.
There are two other questions on the checks below the 10th percentile seem very extreme. Did you try other percentiles? And the other question is, can you remind us of the data size?
For the threshold I use to define the yield shock, I think yeah, the results might be changed if we change the threshold, but I do change the threshold. I do use a lower threshold to define the yield shock. The relative contribution has a little change, not very much. And for the data, do you mean the
the number of data,
open access?
No, the size of the data set.
Oh, the size of the data set. It has about 200 unit by 40 years. So that means about 10,000 yield samples to train the model totally for the 4 regions.